So let's continue. 11.12, a sequence x of n is upsampled by I is equal to 2. It passes through a LTI system h1 of z, and then it is downsampled by t is equal to 2. Can we replace this process with a single LTI system h2 of z? If the answer is positive, determine the system function of this particular system, right? So we can represent this whole of this particular system in a block diagram in this particular form, right? So basically, what happens is that we are passing a signal through an upsampler, and then that is passed through a linear time invariant system, right? That is h1 of z. So in this particular case, it is a low pass filter, and then that is being passed through a downsampler, right? So we can represent this whole particular system into this whole particular system that is given over here in our question as this particular blocks, right? But remember, our system, the low pass filter in this particular case is given as h1 of z. So basically, all the analysis is being done in z transform, right? So we have to analyze this system in z transform form. So just before going on to this, let's touch on some properties of upsampling block and downsampling block, right? So if you have a signal x of z that is being passed through a upsampling block, so what happens is that that x of x is transformed into x of z to the power of capital K, right? So the capital K over here indicates our upsampling integer value, right? So in this particular case, our upsampling integer value is equal to 2 based on our question. So the output of our upscaling block will be basically x of z to the power of 2, right? Then this particular signal is then passed through a linear time invariant system, that is h1 of z, right? So when we are dealing with z transform, when what happens is when a signal passes through another block, what we do is multiply the two functions, right? Two z transformed functions. One of the z transform of the input signal with the transfer function of that block in order to get the output, isn't it? So in this particular case, what happens is our input was x of z, right? So our input was x of z, right? So that is passed through the upsampler block. Now we get x of z squared, right? Since we are upsampling by 2 units. And then that system is passed through a low pass filter or a system h1 of z, right? So when we are passing this signal, how do we get the output? We multiply these two, isn't it? h1 of z and x of z squared, right? So that is the output that we get over here. That is x of z squared times h1 of z, right? Now this is our input to this downsampler block in order to get our output, right? Output y of z, right? So what we can do is use the downsampling property, right? And pass this signal, this input signal, through the downsampling property, using that particular property to obtain our y of z, right? So we can use this particular property over here. We can use this particular property over here, right? This particular property over here to get our y of z, right? So in this particular case, instead of x of z, we'll be using x of z to the power of 2 multiplied by h1 of z, right? And that will be passed through a downsampling block, and that the output will be defined by this particular property over here, right? So our y of z could be represented as half into x of z, h1 of z to the power of half, plus x of z, h1 of z to the power of half, omega to the power of half, right? Whole thing multiplied by half. So this omega is basically the representation of e to the power of minus 2 pi j, right? So now what we can do is we can factor x of z out. So if we factor x of z out, so we'll be left with this particular term over here, right? So based on this, we can see that this particular term over here could be represented by h2 of z, that is basically representing whole of the system, right? So it is basically representing whole of this block, right? So it is not just giving the transfer function of 1 or 2 blocks. It just gives the overall transfer function of this particular system, right? So the answer for this particular question is yes, we can represent the system. We can replace this whole system with a single LTI system, H2 of Z, where H2 of Z is basically given by this particular term over here, right? Okay. Moving on to the next question. That is question number 11.13. Plot the signals of their corresponding spectra for rational sampling rate conversion by I upon D is equal to 5.3. So when we are dealing with the rational sampling, it is basically all this while we have been sampling, upsampling and downsampling using integer values, isn't it? So when we are saying we need to increase the sample, that is being basically multiplying the sample by a certain digit. So we are upsampling basically. So we just basically multiply a particular value or increase the sample size. When we say we want to decrease the down sample, we basically divide the sample, isn't it? We are dividing. So what we can do when we are using rational sampling, what happens is we are able to, all this while we're dealing with all the integer values, now we can deal with all fractional values, all values that could be represented in form of decimal and fraction, right? The decimal values could be represented in fraction values as well. So when we have a fraction, right, when we are sampling in such a manner where we have a rational value, right, we can represent them as I upon D, which is equal to some fraction, right, where the numerator is basically equal to our I and our denominator is basically equal to D, right? So just in case if you are still having some trouble understanding this, please go to chapter 11 of your textbook and go down to section 11.4, where it'll be studying where it will explain you more about sampling rate conversion by a rational factor, right? Now now let's continue with this question. So that was basically about rational sampling, right? Basically rational sampling helps us to sample something of a rational number apart from a integer value, right? So where A is equal to I upon D is equal to 5.3, B is equal to I upon D is equal to 3 upon 5. Assume that the spectrum of the input signal x of 2 occupies the entire range negative pi, which is less than equal to omega x, which is less than equal to pi. So if we were to represent this rather than into a radial form in a normal frequency f, right? So if we were to write this in normal frequency f, so we would have been getting absolute of f is basically less than equal to f of x divided by 2, right? Okay. So if we were to represent the spectrum of x of n, so basically we'll get a triangle, right, ranging from negative f of x upon 2 till f of x upon 2, right? Okay, so the values over here will be f of x upon 2 and negative f of x upon 2, right? Okay, now let's try to understand what happens, right? What happens to this sampling, right? So let me just do this, right, set. Okay, let's go back to this particular block. So when we are sampling, right, you can see that when we upsample it, basically the frequency is being increased, right? So we get a rate of I by f of x, right? That is equal to f, the f of v, that is the output of this particular output sample block, right? So when we are basically passing through a sampling rate of f of x through a upsampler, right? That is the sample rate is being increased, right, by a value of I through an upsampler that gives us I of f of x. And when we pass a signal through a downsampler, basically we are dividing f of x by d, right? So the overall system could be just basically when we are passing through an upsampler and a downsampler, the overall system could be represented by I upon d f of x is equal to f of y, right? So if you are if you are at the first stage, just omit this d. We'll be just reading I of f of x is equal to fy, right? If we are just dealing with the downsampler, just omit the I. In place of I, I mean, you can just omit I, and we're just left with f of x upon d is equal to f of y, right? That is some of the simple things that we will be assuming, right? Or the other way is, rather than omit, if you don't have an upsampler, just let I equal to be 1, right? Just make it 1. So it will become 1 upon d multiplied by f of x is equal to f of y for a downsampler. For an upsampler, in that particular case, we assume that the downsampler is basically 1. So in that particular case, the system output of a upsampler will become I f of x is equal to f of y, right? So that's just the basic concept that the basic theory that you need to understand. Now let me take you back to a example before I touch on to that, right? Since all this while we were familiar with omega, right? What happens to omega input? Just let me first go into the omega input and output part, right? So just for a let's say just for a downsampler part, right? We have a signal that for a downsampler, basically you filter it to avoid aliasing, right? So you filter it and then you pass it to a downsampler. So this is what we will be looking at when we are dealing with omega radial frequency, right? So if you have a signal x of omega, right, and that is being plotted in omega x, you pass it through a low pass filter. That signal will still be in omega x domain, right? So you pass it to a filter, you filter that particular signal. So you're still dealing with the sampling rate of x of omega x, right? And then you get an output that is still omega x, right? For a downsampler, remember, this is a downsampler. There is nothing changing to the sampling of this particular signal, right? Yet it is just being filtered. Nothing is being changing. The sample size remains same. The only sample change happens is after the downsampler, right? So in this particular case, we pass through a filter, and the output in this particular case, in case of omega, it spreads out, right? And in terms of the output, it basically spreads out. Whatever output we had after the filtration, this particular output is being spread out, right? Okay. For a upsampler, basically you can see for an upsampler, it is the other way around. We have a signal, right, for an upsampler in terms of blocks. Let me just show you a block diagram for that. Do I have a block diagram for that? Okay, let's consider this, right? This is an upsampler, right? Just the upsampler and a filter. So what happens is this filter is just for avoiding aliasing, right? So a signal passes through an upsampler, you get an output that passes through a filter, isn't it? So what happens is, in this particular case, you have a signal omega x for an upsampler, right? I'm just telling you in terms of radial domain what is happening. You have a signal that is passing through an upsampler. What happens is the signal starts to fold up, right? In this particular case, for a downsampler, this is actually the signal being input to the downsampler, and this is the output that you are getting. It is basically spreading out. For the upsampler, it is basically what is happening is it is basically folding up, right? Okay. So when the what do you say? When the number of samples changes, the domain it is in, it also changes. So in this particular case, it was in terms of omega x. Now it has changed into omega y. This is why this is happening, because the amount of samples are being changed as well, right? Now, these are just the properties of upsample and downsample when we are plotting in terms of omega, right? Okay, so you can see, can I have a general property of these? Let me see. Just hold on. Just look. Let me look for a. Let me look for a system. Maybe I have that particular system, right? Okay, so I found the notes over here, right? This is from Deepak Kundra, right? From University of Toronto, right? You can look it up on the internet. So just a general representation of the relationship uh, between the sampling frequency, right? In terms of omega and in terms of the sampling rates of Y signal and X signal, right? It is basically related by omega Y is equal to dy upon dx, omega X, which is equal to d upon I, right? D is our downsampling value and I is our upsampling value, right? Multiplied by omega X, right? Just a quick, you can also write this as another property is, okay, let me write it down. Yeah. So basically, what this tx and ty could be also written as ty, right? Wait, is this? Okay. So basically, ty upon dx is also written as, can be written as, if we consider that our f of x is basically equal to 1 upon dx and our f of y is basically equal to 1 upon dy, then dy upon dx is basically equal to f of x upon f y, which is equal to, it is equal to d upon I. Okay, this is just a general property. Okay, anyways, let's continue, right? So this was just with the terms of omega, but now you can see, right? If in textbook do I have that? Yeah, I should be having that, right? So in terms of, in the textbook, you can see whatever is happening in omega value, it is opposite in frequency, like normal linear frequency, right? So when we are dealing with a frequency variable, when we are not dealing with radians, you can see this is opposite to each other, right? When we had f of y is equal to f of x upon d, for omega part, it will be omega y is equal to d upon omega x, isn't it? So basically what it is telling us that these signals start to behave in a different manner, right? When we are using f or d, the signals will behave, I mean, rather than folding, it will start to it will start to expand, and if it was folding, it will start to fold, right? So just before touching on to this in terms of f of x, right? So let's just see some other notes, right? Let me just show you another note that is from okay, here you go, right? So now if we were to use a in terms of normal frequency, what happens is when we are passing through a low pass filter and then we get an output, right? Output of that through a, when we pass it through an upsampler and then we pass it through a filtration block, this is the output that we are getting, right? So just in case if you want to touch on upsampling and downsampling to further study on this, please go onto this particular website. This is from the website of EDN, right? It is a note by EDN, right? So you can just go onto this particular website and just go and read on this further, right? So you can see in terms of normal frequency, what is happening is that now if you had a signal, right, x in terms of the frequency was in terms of f, right, rather than in terms of radians, it was just in ordinary frequency. The frequency response is given as such, right? That is expanding from f of s, f of x, f of y, f of z, right? So basically what is happening is that now if you had a signal, right, x in terms of the frequency was in terms of f, right, rather than in terms of radians, it was just in ordinary frequency. The frequency response is given as such, right? That is expanding from f of s upon 2 till f of s upon 2, right? In our case, it is f of x upon 2 and f of x upon 2, right? It is ranging from negative f of x upon 2 till positive f of x upon 2, right? Then if you pass it through the upsampler, what happens is that the signal starts to, what happens? The signal starts to fold up in normal frequency, right? In normal frequency, the signal starts to fold up, right? This is in terms of the output frequency, right? So the signal starts to fold up, right? And then what happens is then it is being passed through a sampling block, I mean, through a filter block, and then this is the output that we get, right? Now, remember, this is now this particular part has been translated, right? This particular block has been shifted to, I mean, it has been normalized to, in terms of, it has been normalized in terms of L, right? In terms of the output frequency, right? F of S of L in this particular case. In our case, it will be normalized to Fy, right? The same goes for the downsampling part. Let me show you the downsampling part. So basically, you can see that the output of the downsampling, for a upsampling, it is folding up and it is still in the frequency domain, right? In terms of f of s, right? It is still in terms of f of s before it is filtered out, right? So that is for that. For a downsampler, what happens is that you pass a signal, right? It is being filtered, and then what happens is that particular signal is being filtered out, and then it passes through a downsampler, isn't it? So when it passes through a downsampling block, what happens is that the frequency, when you normalize it, the frequency starts to, or when you are starting to represent it in terms of how do you say, in terms of normalized frequency, we get we can see the signal has been folded, right? Again, if you want to read more on this, we are just going to use this particular concept in order to draw the output of the rational sampling block, right? So this is the property, another property that we are going to use in terms of normal frequency rather than the radiant frequency, right? So going back to our question, we had a signal that ranges from negative pi is less than equal to omega x, which is less than equal to pi. So representing in terms of normal frequency rather than radians, it will be f of x is, f is basically less than, just let me write it over here. So basically converting this into frequency, normal frequency, it will be just f is basically less than equal to f of x upon 2, right? And that this particular part has been converted, so we'll be getting an out, then we are passing through an upsampler, right? Whatever signal we had, we are passing through the upsampling block. So based on this particular where am I? Oh, excuse me, I forgot to take you back, right? Let me take you back to the notes, I mean to our particular question over here, right? So I've taken you back to the question, right? So in this particular case, this particular part over here, it is given in terms of radians. We convert it to frequency. This is basically f is less than f of x upon 2, right? Okay. So this is converted into this. So the frequency response of x of n in terms of normal frequency f, right, is going to give us negative f of x upon 2 till f of x upon 2, right? Okay. Now we have a signal x of f of such, right? The frequency response of x in terms of f, in terms of normal f frequency, it is given like this, right? Now, if you have that signal, right, it is basically similar to this particular signal that we have over here. Let me share you that particular screen. Okay, let me take you back here. So for an upsampler, right, this is what is happening here. An upsampler, what happens when you pass it through the upsampling block? What happens to the signal? It expands and it starts to repeat up till f. This output signal is equal to L times fs, right? So in our case, our L is equal to what? Our L is equal to 5, isn't it? So basically we'll have the signal, right? F of x in place of f of s, it is f of x. So we have this signal already, right? From the x of f part, right? It is basically the same thing that we have drawn, right? In place of f of s, we have f of x, right? So this particular signal, this particular triangle is being passed through the upsampling block. So we have this particular type of signal, and it continues up till L times f of s, isn't it? So taking you back, you can see that it is being repeated, isn't it? Up till f of s is equal to L times f of s, right? So in this particular case, what will happen is, if I take you back to the solution, you can see this is what happens. We are taking that particular triangle, and that particular triangle repeats or overlaps up till f times f of x, isn't it? Like in place of f of s, we were using in place of f of s that is given in that particular sample, we are using f of x, and it will continue up till L times f of x. So L in this particular case is particularly our I value, so it is 5. So it will continue up till 5 times f of x, right? So our signal was given only up till here, right? This particular point over here, right? Now we are expanding it up till 5 times the total range of that, right? So 5 f of x, right? So our signal was only given up till here. So we just take that, we multiply the sampling frequency, that is f of x, multiplying that by the L value or I value, that is 5. So we'll repeat that particular signal up till 5 of x, right? So this is what we are getting. Again, that is based on this particular example that I showed, right? It's easier to understand, right? It repeats itself, right? Now, what happens is, now that we have this, right? Now what we'll do is, now we'll go back to this. Now what happens is, like I showed you over here in this particular case, right? A whole multi-rate conversion happens using this particular signal, right? Or rational conversion happens using this particular signal. We have an upscaler, that a low-pass filter, and then we have a downsampler. This low-pass filter is basically designed by half the minimum value of f of x, the input frequency f of x, and half the minimum of both of these, the minimum of f of x and minimum of f of y, right? So the filter is basically designed by that. So we have a filter value half minimum of f of x, f of y. So this particular point over here is basically half of minimum of f of x and f of y, right? Okay, so we passed this particular signal through this particular block, right? And we can see what happens is that this particular in this particular case, it filters out all this particular signal, right? So it passes through a low pass filter and it filters out this signal. So we have only this where the filter is passing through the, we have a signal that is passing through the pass band, and the rest of the signal are omitted through, during the stop band pass, right? So we obtain, after the filter, we obtain these two triangles, right? Only at this particular points, right? Of this particular signal, right? This is the interpolated signal, right? And this is after filtering. And then this filtered signal is then, that filtered signal is then passed on to the downsampler, right? Downsampler. So let me take you back to this particular case in the in the notes that I showed you, right, in this particular website, you can see that when we are passing through a downsampler, we have this something filtered signal over here. Similar to our case, we have a filtered signal, and we pass it through a downsampler. So what happens is that the particular signal normalized, right? When we normalize the particular signal, we start to see that a signal is now being repeated up till m times the f of x part, right? Fy part. This is because after the signal, this f of s, excuse me. So basically this particular part, the output has been normalized in terms of Fy, right? So, or in terms of the output frequency. So when normalized in terms of the output frequency, so it is basically repeating itself, isn't it? So if we go back here into our particular question, you can see what will happen is that this output will now repeat itself and be evenly distributed in terms of the y frequency or normalized frequency Fy, right? So that is basically multiplying 3 with Fy, right? Okay. So, or the other way is that when we are trying to represent it in terms of Fy, so d times Fy, so you can see that is increasing this Fy. So it is starting to repeat itself, right? Okay. So we'll be having 3 sets of that. The same process for the other one, right? When I upon d is equal to 3.5. Again, we have the same triangle. Remember, we had the same triangle. So that same triangle is now, when we are passing through a interpolation block, right? Or when we are in upsampling, the output will be basically increased, right? So it is basically repeating itself 3 times, right? So that is going to happen 1, 2, 3 times, right? And then we design a filter that has to be the minimum of f of x and f of y, right? So whatever minimum value we have, this particular point will be minimum of that, right? And then this particular signal will be passed through that. So based on this particular filter, you can see that these particular parts are exceeding. So only this from here till here will be passed through. So you'll be getting something like this, right? As your output frequency, right? Now, what happens is that once we have this, the output in terms of normalized frequency Fy is going to give us, it is going to be folded, right? It will be evenly folded how many times? Times 5, right? All this was in terms of f of x, right? In sampling frequency f of x. Now, if we represent it in terms of f of y, rather than spreading, it will start to overlap itself 5 times, right? So 1, 2, 3, 4, 5, right? So this is the graph you have. Again, if you have still trouble understanding this, please read your textbook, chapter 11.4, right? Sampling rate conversion by a rational factor. That is in this particular section 11.4 of your textbook. And you can also check this website. I would recommend this website for better understanding of how we represent it in terms of a normal frequency, right? So this website is another recommendation. Okay, so you can understand about upsampling and downsampling and how it works, right? Okay, so that's it for this week's tutorial. See you next week, right?